Hello everybody, I am Lup from sunny Singapore. This presentation will look a little unusual to most NuttX developers. We will do an experimental exploration of NuttX log analysis with a functional programming language called PureScript. If you would like to download the presentation slides, please head over to this link, logyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation transcript, articles, and source code are available at that link. Today, we can get real-time logs from our NuttX devices like Ox64 RISC-V single-board computer and the emulator for Ox64 SBC. What if we could analyze the NuttX logs in real time and do this all inside a web browser? Today, we shall explore this with PureScript, the functional programming language. NuttX development can get super challenging. It takes a while to figure out what is really happening inside the NuttX kernel and NuttX apps. Can we improve the NuttX Developer Experience with functional programming tools like PureScript, or maybe newer hardware? We will chat about this. I promise to stop myself from getting too deep into PureScript. PureScript will feel like listening to jazz music for the very first time. It is interesting. Not 100% sure if everybody will like it, but it is a fun new way to think about the things that we do every day. We are watching a demo of our experimental NuttX log analyzer. Suppose we are testing a NuttX app and it crashes with this horrific crash dump. At the right, something helpful appears. Our log analyzer extracts the RISC-V exception from the NuttX crash dump, and it explains what's causing this RISC-V exception in friendly words, which is great for folks new to RISC-V. But exactly what code caused the crash? Clicking the exception address will show us the NuttX disassembly of the questionable code, which is hyperlinked to the NuttX source code from our GitHub repository. See the stack trace at the right? The stack dump is also helpfully hyperlinked to the NuttX disassembly and the NuttX source code. This will work for NuttX kernel and NuttX apps, with some limitations, of course. Hopefully, our NuttX log analyzer will be super helpful for folks doing NuttX development for the very first time. Now we go inside our experimental log analyzer to understand how PureScript makes sense of all this NuttX crash dump. So what just happened in our demo? NuttX boots on our emulator for Ox64 BL808 single-board computer and starts our NuttX app, which happens to be the Quick.js JavaScript interpreter. Our NuttX app crashes with a RISC-V exception. The terminal output shows pages and pages of logs as seen by NuttX developers today. We talk about the Ox64 Emulator and Quick.js JavaScript engine in another presentation. Please check out the presentations here. Then our demo shows something totally new. We have a NuttX log parser that shows the RISC-V exception info and explains the RISC-V exception. This is a load page fault. The code at this address tried to access the data at this address, which is invalid. That's why it failed. This was automatically extracted from the pages and pages of crash logs, which is super helpful for folks new to RISC-V platforms. But why did our NuttX app crash? What is the source code leading to the crash? As NuttX developers, we are used to seeing pages and pages of stack dumps. What if there was a way to click an address in a stack dump and jump to a NuttX source code? Yep, we did it. The stack dump is now clickable. Clicking an address in a stack dump brings us to the NuttX disassembly, which links to the NuttX source code. Everything is now point and click. Thanks to the NuttX Log Parser, we have extracted and interpreted all the interesting bits, the exception info, exception explanation, and stack dump, hyperlink to the NuttX source code to make this really helpful for NuttX developers. This sounds like a dream come true for NuttX developers. How did we make all this happen? What are the limitations, and why do this in PureScript? We begin by understanding how our NuttX Log Parser explains a RISC-V exception by analyzing the NuttX crash dump. In NuttX, we normally see this kind of RISC-V exception. Imagine that I am a fresh new developer coding on a RISC-V board for the very first time. I will probably ask, what exactly MCOS, EPC, MTVal? Well, a seasoned RISC-V developer would say, MCOS is the cause of exception, EPC is the exception program counter, MTVal is the exception value. Not quite so obvious if we are stuck staring at a crash dump. That is why we wrote a script to explain the RISC-V exception in friendly words and in the correct context. We hit a load page fault, our code at this address, tried to access this data address, which is invalid, and it failed. This is how we coded in PureScript. We explain RISC-V exception 13 with this EPC exception program counter and this MTVal exception value. Our PureScript code will concatenate these strings and values together with this double arrow thingy that looks like a diamond. We explain the other RISC-V exceptions the same way. This is how we explain RISC-V exception 12. Yeah, this explanation is still incomplete, but you get the idea. And this is the catch-all that explains all other RISC-V exceptions. All of this looks like a tidy bunch of rules that will explain RISC-V exceptions in a declarative and rules-based way. Looks a bit like makefile or kconfig or prolog. We could have done all this in C or Python or JavaScript, but it probably won't look as neat and tidy. At the top of our PureScript function is this thing that looks totally alien. Just think of it as a function declaration in C. This says that explain exception is a function that accepts three parameters, MCOS, EPC, MTVal, and returns a string that explains the exception. Okay, it looks like we have 4 parameters, but it's actually 3 plus 1 because of the way functions are defined in JavaScript, something called currying. Our demo runs in a web browser with JavaScript. Our explain rules are in PureScript. Can we call PureScript from JavaScript? Yep, this is one of the coolest things of PureScript. Anything we code in PureScript can be called from JavaScript, right inside our web browser. Our PureScript function for explain exception that we saw earlier, it behaves like a typical JavaScript function that we can call directly from our web browser. This is how we call explain exception from JavaScript, passing the exception number, exception program counter, and exception data address. The return exception is returned as a string in JavaScript. All of us have bits of NuttX troubleshooting skills locked away deep inside our brains, like how to read RISC-V exceptions, what the exception means, what causes these exceptions, how we fix them. All these NuttX troubleshooting skills why don't we express them in code for the NuttX community to execute and reuse? PureScript looks like a neat way to express our troubleshooting skills. Other functional programming languages will probably work too. Ready for a bit more PureScript? This is how we parse and extract the RISC-V exception from the stream of NuttX logs. All of this happens in real time. Earlier we saw PureScript explaining our RISC-V exception. But how did we get the RISC-V exception? The exception cause, exception program counter, exception value? Well, they appear in the NuttX log like this. We wrote a string parser in PureScript to extract the exception info from the NuttX log in real time. PureScript really shines for string parsing, as we shall soon see. Here is our string matching pattern. This pattern will search for the literal string RISC-V exception, skip some spaces, search for literal string exception, skip more spaces, and discard the whole matched string. That is what void means. In functional programming languages like PureScript, we tend to see plenty of brackets or parentheses. That is why we have shortcuts like $. When we write $, something, something, it is actually a shortcut for bracket something, something. So this chunk of code here doesn't need to be wrapped with brackets. A single dollar will do. Next comes a regular expression for string matching. We use this regular expression to match the exception number and return it as the mcos string. Then we skip the comma and we skip more spaces. Finally, we return the interesting bits of exception info, the exception cause, converted from hexadecimal to integer, the exception program counter without the 0 prefix, and the exception value without the 0 prefix. There is a complicated reason why we say that this is pure. It has to do with side effects and monads, but we won't go too deep into PureScript in this presentation, I promise. One last cute trick in PureScript. Sometimes we write back quotes or back ticks like this from maybe. Well, something backtick something is actually equivalent to bracket something something. Okay, enough PureScript for today. Hopping on to JavaScript. We have created a string parser in PureScript that passes a RISC-V exception. This is how we call the string parser from JavaScript. We pass the exception string to PureScript, and we get this JSON result with the exception info. Remember our RISC-V exception explainer from earlier? It works great with our exception parser. Thus, we have a PureScript function that extracts the exception info and another PureScript function that will accept the exception info and explain it. Once again, how and why are we using PureScript? We use PureScript to write the rules to extract the exception info, to explain the exception in a high-level way. We use JavaScript to pass around the nuggets of info in and out of PureScript. It feels that we're using PureScript to enrich each bit of info with our NuttX troubleshooting skills, so that everything makes more sense to NuttX developers. This is how we create a smarter log parser for NuttX. We saw our NuttX troubleshooting skills expressed as high-level rules in PureScript, but the rules need raw data and NuttX logs to work on. How do we feed the NuttX logs to the PureScript functions in real time? For Ox64, this gets a little easier because we have the Ox64 Emulator running inside a web browser, which will let us pass NuttX logs from Ox64 Emulator to PureScript in real time, line by line. Inside our JavaScript, this is how we pass and explain the NuttX logs by calling PureScript. Everything happens inside our web browser, thanks to the seamless integration between JavaScript and PureScript. This might become more difficult with other functional programming languages. What about a real NuttX device, like the actual Ox64 single-board computer? Well, our web browser can talk to Ox64 serial console directly over the USB serial port thanks to the Web Serial API. The web browser JavaScript that we saw earlier, we could potentially reuse everything and pass the NuttX logs from Ox64 SBC to our PureScript log parser. We explained the Web Serial API in the presentation on Ox64 SBC. Check out the presentation here. Here is a quick look at Web Serial API controlling a real Ox64 SBC from within a web browser. With the Web Serial API, our web browser can talk directly to serial devices connected to our computer, like this Ox64 SBC. Our web browser JavaScript can then send NSH commands to Ox64 and capture the serial output. This is how we might run our NuttX log analyzer with a real NuttX device. One final mystery in our NuttX log parser. How did we hyperlink the stack dump to the NuttX source code? How did we figure out whether a NuttX address points to code, data, BSS heap, or it's just pointing to some random garbage? Again, we have rules for that written in PureScript. We match the NuttX addresses with regular expressions. This rule says that 502 something something comes from NuttX kernel code. This rule says that 800 something something comes from NuttX app code. We make the distinction between NuttX kernel and NuttX app because we need to hyperlink to the correct source code. Everything else points to random garbage. We won't hyperlink to the source code. This is how our JavaScript calls PureScript to match a NuttX address and figure out whether it points to NuttX kernel code, NuttX app code, or just random hot garbage. Okay, it is a little disturbing that we are hard coding address patterns for this demo. Our troubleshooting rules might evolve. Depends how folks will use our NuttX log parser. The address patterns will be different from RISC-V and ARM platforms. How will we customize the address patterns? That is why we have an online PureScript compiler that will allow troubleshooting rules to be tweaked and tested easily across all NuttX platforms. What exactly is this online PureScript compiler? How will it compile the troubleshooting rules for our NuttX log analyzer? Let us take a peek. Remember the rules that will identify an address, whether it is kernel or app? The rules are located at the left in our online PureScript compiler. And we tweak the rule that will identify an address. Notice that the results are immediately reflected at the right side. This will make it simpler to create and maintain the NuttX troubleshooting rules in our log analyzer. The next part of our NuttX log parser will be helpful for folks who work with NuttX disassembly. Given a NuttX address like this, how do we show the NuttX disassembly? Our solution is to chunk up the NuttX disassembly into many small files grouped by NuttX address. So this NuttX address will appear in this NuttX disassembly file, which gets hyperlinked into our NuttX log display whenever this address is displayed. How do we split a NuttX disassembly into smaller chunk files? We begin with the ELF executables for NuttX kernel and NuttX apps. And we export the RISC-V disassembly into a file like this, qjs.s. We wrote a NuttX disassembly chunker in Rust that will take a huge NuttX disassembly like qjs.s and split it into smaller disassembly chunk files that are grouped by NuttX address. So this disassembly address goes into this chunk file and so on. This is how we're able to render the NuttX disassembly for any NuttX address. This works because we have disassembly files in small chunks that we have loaded into our web server. What about hyperlinking to the NuttX source code? Inside the NuttX disassembly, we have the path name and the line number of the source code. Our JavaScript will convert these into a hyperlink that will jump into the line of source code in the NuttX GitHub repository. All this will save us lots of time. No more searching and grabbing for the NuttX source code. Just click and the source code appears. Back to our original NuttX horror story. We ran this NuttX app and triggered this strange NuttX crash dump that looped forever. What caused this strange problem? This was before we created the NuttX log parser. We had to search and grab for every single NuttX address that appears in the NuttX crash dump. Jumping from NuttX disassembly to NuttX source code again and again and again. It took us a while to realize that this crash could never possibly happen. There was a clear sign that we missed, the loopy crash dump, which means that the NuttX stack was full. This is why we need a smarter log parser that will catch these common problems and prevent NuttX developers from falling into these traps. And that is all for our experimental log parser. Given real-time logs from a NuttX emulator or a NuttX device, it extracts the exception info and explains the exception. It produces the clickable stack dump that links to the NuttX disassembly, which links to the NuttX source code. The NuttX troubleshooting rules are still evolving, so we have an online compiler that will compile our NuttX rules and run them inside our log parser. Okay, thanks, but why are we doing all this? Why are we making a smarty pants log analyzer for NuttX? Why are we doing rules-based programming with functional programming languages like PureScript? Who are we really trying to help? Well, we're doing all this for NuttX developers, of course. We wrap up our presentation today by reflecting on the NuttX Developer Experience, lessons that we have learned from Ox64 single board computer, and why we are hopping sideways to a newer single board computer, Softgo SG2000, and Milk5 Duo S. I think NuttX on Ox64 has been somewhat successful. At least I see some folks using it. What is it about Ox64 that makes it appealing to NuttX developers? I have a few hypotheses. I think RISC-V 64-bit might be easier to learn, which is great because we will see many RISC-V boards based on the RISC-V CPU, T8C906 CPU. Ox64 SBC is highly affordable at $8, so that helps. Though looking back at Ox64, I would have preferred a $10 board with an Ethernet port, so we don't swap the microSD so often. We will talk about SG2000 in a while. Embedded development seems to be moving away from plain old OpenOCD and GDB, like my good old days with STM32 Blue Pill. Today, we are working with RISC-V SBCs with network booting over TFTP, plus a NuttX log analyzer that runs in a web browser and links to the NuttX source code. Our development machines are getting more powerful. Today, we can run Ox64 Emulator on our computers and complete the OS test in seconds. Could this be a sea change in the way we do NuttX development? If you're looking for a more powerful RISC-V board, check out the CanMV K230 based on the Kendrite K230 SoC, which runs on T8C908 CPU, which is the upsized version of Ox64 and T8C906 CPU. My good friend YF has been super successful with the porting of NuttX to the Kendrite K230 SoC. Maybe someday we can use the onboard camera and run some image recognition apps directly from NuttX. Porting NuttX to K230 was an interesting experience. YF is based in China, I am in Singapore. Very often we would stare at the NuttX crash dumps and figure out what went wrong. There's so much NuttX expertise locked away deep inside my brains. I feel kind of bad that I couldn't share my brains with YF and make the NuttX porting a little easier. This is my motivation for creating the NuttX log analyzer that I presented today. Now we head back down to a cheaper $10 board, the Milk5 Duo S, based on the Softgo SG2000 SoC. We expect plenty of new SBCs to be released soon, with the Softgo SG2000 SoC inside. That is why I ported NuttX to SG2000. This is a $10 board with Ethernet port, which will boot NuttX over the network. No more swapping micro SD cards again and again and again. The pins are all exposed, no soldering needed, easy to attach sensors and actuators. Reminds me of Arduino Uno actually. There is a more powerful SG2002 SoC that comes with a smarter tensor processing unit, which might work better for image recognition. This board comes with a MIPI CSI input for digital cameras. I am now upstreaming NuttX for SG2000, and I am building the NuttX emulator for SG2000. All the nice things we've learned for Ox64 SBC, we're doing the exact same things for SG2000. Check out the details in the article here. Here is a sneak peek of NuttX booting on an SG2000 SBC, the Milk5 Duo S. This is a $10 SBC with an Ethernet port. So we see our SBC booting NuttX over the network with TFTP. No more swapping of micro SD cards. I highly recommend booting NuttX over the network with U-Boot bootloader. It makes NuttX kernel development so much quicker. We conclude today's presentation with LLMs, large language models. Can they help with NuttX troubleshooting? Today, I used the RISC-V disassembly of NuttX kernel for troubleshooting all kinds of problems because the NuttX disassembly has everything inside. Who calls what, macros all fully expanded with links to the source code, like we saw in the presentation today. But the NuttX disassembly has way too many details inside for human brains to ingest. Maybe an artificial brain will help? So we politely ask the AI, here is my enormous NuttX disassembly file. Please digest it and answer my question. How will the NuttX boot code start our NuttX shell? Tell me very precisely, step by step, what happens exactly when NuttX boots on my device all the way to NuttX shell. Here is the answer from a popular LLM. It looks promising. It seems to know something about NuttX booting on RISC-V devices. Or maybe LLM is just regurgitating my NuttX articles. For folks who can't distinguish LLM from MLM, no worries. We will let you know when this stuff is mature enough for daily use. If you are keen to learn more about PureScript or try out the new port of NuttX to Softgo SG2000, please check out the articles here. We have 2 more presentations on Ox64 SBC about porting NuttX to Ox64 SBC and the tiny Emu emulator for Ox64. Please check out the presentations at this link. Today, we took real-time logs from an emulated NuttX device and did some real-time analysis. It looks feasible, though we might take a while to capture and record our NuttX troubleshooting skills to make the log analysis truly helpful. Now is probably a good time to think about the NuttX Developer Experience. Can we make it better with functional programming tools like PureScript or newer hardware like RISC-V SBCs? Let us work together to make things a little easier for new NuttX developers. Thank you.